Okay, we'll make a start. Good afternoon. Thanks for joining in and welcome to the irrigation webinar series. Today's webinar is part one of a two-part sub-series focusing on reading climate drivers for better farm decisions. And today's webinar is all about reading climate drivers. My name's Rob O'Connor. I work for AgVic based at Echuca in the irrigation team. I'd also just like to give a mention to Joe Braden, AgVic Tatura, who's working busily behind the scenes to keep the webinar going. Also just acknowledging I'm coming to you from Yorta country and acknowledge long history and ongoing connection of Yorta to the land and waters in this region. The webinar is being recorded and the recording will be sent out as a link to registered webinar participants, hopefully sometime early next week. If you have a question, please use the Zoom chat function and select co-host, and then I can forward those questions to our speaker, Dale. Questions will be answered at the end of the webinar, and depending how we're going for time, there could be a break, question break during the presentation. We love your questions. We also love your feedback on this webinar series. So there will be a survey at the end of the presentation. And if you could complete that survey, that would be fantastic. And we're aiming to finish at 2 o'clock. The second webinar in this series is on same time, same place next week. And we're focusing on using climate drivers, outlooks, forecasts, and tools in the context of better farming and irrigation decisions, and the current climate outlook will be part of that session as I understand it. Just a quick thank you to our supporters who are the CMAs along the Murray, the water authorities, Gulf Murray Water, Lower Murray Water, Regional Development Victoria, and DECA, including AgVic, and a special mention just to the farmer organisations and agency groups who have helped us to promote this webinar series. Our speaker today is Dale Gray. Dale's a seasonal risk agronomist with AgVic at Bendigo, and I suspect that a lot of people would have seen Dale in action as a speaker or author or general analysis on all things weather and climate. So we're delighted to have you on, Dale.
No worries. Thanks very much, Robbie, and good afternoon, everyone. Greetings from Jara country, the ancestral homelands of the Jar Jar Wurrung people here in north central Victoria, and in particular Bendigo, where I am from. Today we're going to be talking about some of the key climate drivers that affect Victoria, and in particular how they work, what their machinations are that make them tick, and what the effects they've had historically have been. In particular, we're going to be talking about two phenomena that affect the moisture sources for us in our northern areas. The ENSO phenomena, El Nino, La Nina, the Indian Ocean Dipole in the Indian Ocean. And we're going to be talking about some of the moisture trigger ones as well. In particular, we're going to be talking about a phenomena called the Southern Annular Mode, which is spinning around Antarctica. But first, just want to very briefly show people here a picture of the ocean temperature as of a couple of days ago. The ocean is the warmest along the equator, and it is the sun that is driving into that ocean and keeping it hotter than down here near the North and South Pole. The ocean temperature off the coast of Victoria at the moment is 16 and below, a bit chilly. And it's critical to understand that there's no meaningful evaporation off the ocean unless it's above 24 degrees. And that's along this yellow line here. So this zone in here is essentially the engine room of rainfall around the world, where the evaporation off the ocean occurs and where the vast amount of water for rainfall derives from. So I've got a picture up here pointing to 30-degree water up here east of the Solomon Islands and through parts of Indonesia as well and around India. So that's about the warmest we've got there at the moment. What's important to know is that a change from 24 to 25 degrees gives you a small extra increase in evaporation. If you go from 27 to 28 degrees, you get quite a large amount of extra evaporation. If you go from 29 to 30 degrees, you get a crazy amount of extra evaporation. We're not talking a straight line relationship here. So the climate phenomena that we're going to talk about in the north essentially just changed the temperature up here by 1 or 2 degrees, which may seem small, but that's enough to dramatically change the evaporation that's coming off that water body. This is just an image from space showing the the total precipitable water in the air column from the stratosphere down to the ocean in fluorescent green. And that's just showing you that the humidity, the moisture in the atmosphere is in fact pretty closely related to where that warmest ocean actually is. And the warmest bit's in the Western Pacific and the Indian at the moment, and that's where the lion's share of the humid atmosphere is. Occasionally, you get frontal rainfall in storms that's dragging moisture out of the tropics. And sometimes that gets detached in that, and we get a front sort of coming through with no connection to the tropics. But anytime in northern Victoria in particular, on the flatlands where we get over 25 mil of rain, we've pretty much got to get a connection to the tropics to do that. If you're in the mountains, it's a bit different because you can get the mountains to lift things up for you and you can get more rainfall out of systems that perhaps aren't related to frontal systems. So let's talk about ENSO occurring in the Pacific Ocean, a phenomena. This is just a schematic of a normal Pacific Ocean, which occurs half of the time. We often don't talk about that, where the trade winds blow from east to west along the equator. The wind blowing off South America from the east causes the ocean to upwell a little bit cool over here on the coast. And the trade winds blowing to the west hold a patch of sort of warm water up here near the Solomon Islands of Papua New Guinea. And this is where there's evaporation and cloud forming. What we have in the La Nina phenomena is an accentuation of the normal state. And this occurs about a quarter of the time. The trade winds blow from east to west much, much stronger. That upwells much cooler than normal water up here over on the coast of South America, and then it gets pushed across. Those stronger trade winds push water to the north of Australia, much warmer than normal water, and they hold it there. We get a lot more evaporation, we get a lot more cloud, we get much lower pressure to the north of Australia, and we get higher pressure coming down over on the other side. The La Nina phenomena is a coupled ocean atmosphere phenomena where we're looking at changes in both the surface and the depth of the ocean, and we're looking at changes in cloud, wind, and pressure. So there are 5 factors there which make up a La Nina. And El Nino is the exact opposite. In fact, it's a reversal of the normal state. And in fact, we get the trade winds really quite weak. And in fact, in the Western Pacific, we often get the reversal, complete reversal of the trade winds blowing in. Some stronger westerly wind around Papua New Guinea makes the water upwell colder in that area. It's much warmer along a warmer tongue across the Pacific. And we now start to see warmer water happening in the middle of the Pacific, convection, evaporation rising up in that area, cloud forming there, and lower pressure. And we have descending, dense, colder air coming down over northern Australia, causing much higher pressure. So it too has these 5 factors involved in the phenomena. This is just an image of the 2010 La Nina. This is a sea surface temperature chart where you've got warmer water in orange and colder water in blue, and the center of the Pacific coming out from the Ecuadorian region. You can see this cold tongue of cold water here, and that was about 1.5 degrees cooler than normal. The threshold for a La Nina is only 0.8 degrees cooler than normal. Because the trade winds were blowing much stronger, pushing warm water to the north of Australia, you get this classic horseshoe-shaped pattern of warmer water in both the northern and the southern hemisphere. But critically, what happens is that the moisture zones to the northwest and the north and the northeast of Australia are warmer by some 1 to 2 degrees. This is just a map that we use to tell us what's happening with the trade winds. Everywhere you see an arrow, and the size is where the wind is going from. And the size of the arrow shows you how much stronger the wind is. And so normally you'd be seeing, if there's no arrows, it means the wind's normal. But in the whole western half of the Pacific here, you can see much stronger than normal wind. The background color is sea surface temperature. So this is the coldness, and there's that warmness starting to appear over there on the far western side. Remember, our coldness at the surface is being maintained by a massive amount of colder water to depth. This is a sub-cross section across the equator. You've got Papua New Guinea over here and Ecuador over here to a depth of 400 meters. And this is showing much colder than normal water to depth, to sort of 200 meters underneath. And so when that water's upwelling over on this side of Ecuador with those trade winds blowing stronger, it's upwelling much, much colder and being blown across almost 2/3 of the way across the Pacific. I like to think that's like the thermostat in the freezer. If you want to keep it cold, you need to turn the thermostat down, and the undersea of the ocean is that thermostat helping to keep the ocean surface cool. This is the pattern we get in the cloud in La Nina, the junction of the date line and the equator, a complete lack of cloud in brown with much clearer than normal skies over in this zone, and that warmer water to the north of us evaporating more water and putting a lot more evaporation and condensation into the atmosphere to the north of us, appearing as a heap more cloud. This is just a pressure chart for December of 2010. Doesn't show it overly strongly, but it is still a change in that we've got lower than the average pressure at Darwin, and particularly down south of Australia and out here in the Indian Ocean. And we've got higher than normal pressure at Tahiti, just here. The Southern Oscillation Index is the measure of the difference between Tahiti minus Darwin pressure. And when we've got low pressure at Darwin and high pressure at Tahiti, the Southern Oscillation Index is positive. And when it's above +8, we would indicate that that is where the pressure patterns are indicative of La Nina. In particular, you can see the pressure in the South Pacific here is a lot higher when we have La Nina. This is just some statistics for that 2010 event showing the rainfall deciles across Australia, whereas you can see that Western Australia had a actually really nasty drought in that year. So La Ninas manifest themselves differently into who's getting the wet bit. Normally it's Eastern Australia. It doesn't often creep this far over, but often there's a disconnect between Western Australia and Victoria in this phenomena. This is just some rainfall tercile graphs here in the years that have been La Nina at Kyabram in northern Victoria, where it's been 46% of the time when we've had 33 La Ninas, 46% of the time the rainfall has been in the highest third of records. And 18% of the time it's been in the lowest third of records. So La Nina does not equal floods. It hasn't ever equaled floods. Every option is on the cards. Anything could happen, but it's just that the chances of drier are much more decreased, and the chances of wetter are much more increased. This is August to October. If we look at July to November across Victoria, we can see perhaps a slightly stronger influence, and you can see that only with the exception of East Gippsland, which sort of is a third, that this phenomena is, occurring right across Victoria and southern New South Wales, and into Tasmania and South Australia for that matter as well. Let's have a look at the cousin El Nino now. A warming in the Pacific Ocean in the centre here of plus 0.8 degrees or more. This was the 2015 El Nino from October. This temperature in here, I think, was about 1.5 to 2 degrees warmer than normal. But more importantly, it's the colder than normal water to the north of Australia that is the problem. You can see the trade winds, which were blowing very strongly from east to west in October of 2015, were completely reversed and completely cranking in that opposite direction. Papua New Guinea here blowing out into the centre Pacific and upwelling the colder water to the north of Australia and pushing that warmer water into the centre. The other thing these reverse trade winds do is that the trade winds that are coming from the east crash in with this reverse trade winds from the west, and the wind is really calm in the central Pacific. And because the ocean is calm, it allows the sun to get in and to heat it up even more because of a lack of actual wave disturbance. You can see the ocean to depth in El Nino is much warmer, and this is like putting the gas flame on your cooker up, that if you're trying to maintain a hot surface, well, you need to have the undersea really much warmer as well. And you can see that we had colder water over in the Western Pacific that was upwelling as the wind pushed from west and causing that to flip up colder to the north. This is the cloud pattern. An abundance of cloud now sits at the end of that warm tongue that comes out, where there's just an abundance of cloud at the junction of the date line. And now we've got a complete lack of cloud to the north of Australia. The pressure pattern completely changes. We now have high pressure at Darwin and also over southern Australia. We have lower pressure out in the South Pacific and in particular at Tahiti. Tahiti minus Darwin pressure, small number minus big number gives you a negative number, and the SOI would be negative. Anything less than -8 would be indicative of an El Nino-like pressure pattern in the Pacific. These are some of the statistics for El Nino. This was the 2015 one. You can see it manifested through Queensland, northern New South Wales, not so much central New South Wales at all, had a pretty normal season, but Victoria was certainly dry, the southeast of SA and Tasmania as well. The statistics for Kyabram showed that when you have an El Nino, 77% of the time the rainfall has been in the lowest third of records, and 6% of the time it's been wet. That's a pretty big skewing of the roulette wheel of chance when you have an El Nino season. If you look at the July to November rainfall, you can see that, that 75% chance still kind of exists. And it's, it manifests itself once again over pretty much the whole of the region, except for East Gippsland. Let's move now to a different ocean, to the Indian Ocean, where we see a phenomenon called the IOD, the Indian Ocean Dipole. And when it's behaving normally, we've got trade winds sort of swinging in here from east to west very gently. The warmer waters in around Indonesia, this is where it's normally evaporating a bit more and forming a little bit more cloud. That's the situation normal, and that happens half of the time. What is sometimes, well, sort of a reversal of this pattern is the positive Indian Ocean dipole, where we have colder than normal water off Indonesia and to the north of Australia, warmer than normal water off the Horn of Africa and Kenya and Somalia. This is where the warm water is. This is where the atmosphere is rising and the evaporation. This is where the cloud is forming. This is where there's lower pressure. And we get descending cold, high pressure zone forming up here over Indonesia. And you've got this upwelling of colder water occurring because the wind is blowing stronger from the east, causing it to flip up cooler in this zone and pushing it over and holding it warmer off the coast of Africa. So this phenomena too is the same as ENSO in that it's occurring at the surface and the depth, and there's cloud and wind and pressure indicators as well. The negative phase of the IOD is the opposite of the positive. It's really an accentuation of the normal pattern. You've got much stronger than normal westerly wind coming across the Indian Ocean. You've got warmer than normal water around Indonesia and Sumatra, and colder than normal water upwelling from underneath as a result of that wind pushing stronger in from the west, flipping that off the coast of Africa. Now you've got warmer water, more evaporation, more cloud and lower pressure occurring to the northwest of Australia, and you've got denser, colder, heavier air coming down, forming higher pressure over off the coast of Africa. This is a picture of the 2006 positive IOD, colder than normal water in this zone that we monitor in this box here, and warmer than normal water off this zone over here. The dipole mode index is the thing that we use to measure the difference between these two boxes of water. And when the difference is 0.4 degrees, that's deemed a positive IOD. And that's a very small difference indeed between this area of water and here to cause that phenomena to be kicking off and going. The cloud pattern signature is probably the best one you see, but what do IOD events look like? The positive IOD gives this eye of a lack of clouds sitting over top of that box of colder water off Sumatra in here, in Indonesia. That's the classic signal. And the positive IOD is the best known killer of northwest cloud band activity coming down into southeastern Australia. So you get a lot less northwest cloud bands coming down over Port Hedland and Broome when you have this phenomena. Here's the pressure pattern that was in existence at that time. And we had just slightly higher pressure out over this area here and slightly lower pressure off the coast of Kenya. Those differences there are minor, but they're enough to, on average, sort of kick the pattern going along, is that the airflow is towards this direction. These are the stats. This was the 2006 spring. Was really quite dry through South Australia, Victoria, and southeastern New South Wales and Tasmania. When we have positive IOD years and have at Kyabram, 64% of the time the rainfall's been in the lowest third. And you can see that once again, with the exception of East Gippsland, Far East Gippsland, that this phenomena is very broad scale across southeastern Australia. Looking at the negative IOD, we've got much warmer than normal water now in this box off Sumatra. This is the 2016 event, which up until last year was the strongest event that we'd had for some time. We didn't really have, it was more normal to cooler water sitting off here, but often with these phenomena, both with ENSO and the IOD, it's about a differential. As long as somewhere is much warmer than somewhere else, it can cause the wind flow to change. And so that's what we saw in this event. A negative IOD is when the difference between this box of water and this one is cooler by 0.4 degrees. a classic pattern for the cloud pattern for a negative IOD, an abundance of cloud, a big eye of an abundance of cloud sitting over the top of that that box that we monitor off Sumatra and into Java of Indonesia. And the negative IOD is the best known bringer of northwest cloud bands down into southeastern Australia. This was the sea level pressure at that time. Basically, there was sort of higher pressure from Sumatra this way, but there was just generally slightly lower pressure across the whole Indian Ocean basin. I would have thought that the signal was going to be a bit stronger than that, but I couldn't find a map that actually necessarily showed that. But sometimes you can occasionally see higher pressure off the coast of Africa as well when you have a negative IOD. This is the data for the 2016 negative IOD. Really caused it to be wetter over much of Australia, just a little bit of drier in parts of the southwest of WA. A much stronger chance of it being in the wettest third of records. And if we look at this is August to November rainfall here again, you can see that some of these pie charts really get quite strong. In fact, if we look at August to October rainfall, there's an area of what you call the southwest quarter of Victoria for whom they've never had rainfall in the lowest third of records when it has been a negative IOD. It's been a very strong climate driver, causing it likely to be average or wetter in this kind of zone over here. Which brings us to our final climate driver. Those two that we've talked about are all about changing the ocean temperature to the north of us and switching off and on the moisture zone. The southern annular mode is what's occurring around Antarctica. Here's Australia in here, Antarctica, and the westerly winds spin around Antarctica, blowing really, really strongly. And the southern annular mode is a measure, a crude measure really, of what's going on around here. And there's about 6 locations that they measure the pressure difference at 65 degrees latitude. Most of these are the Antarctic bases, places like Mawson and Davis and Russian and French ones. And then the other locations around here are islands or Hobart. There's somewhere over here in Argentina. And it's just the difference between the two latitudes here between 40 and 65. But what this climate driver does is that sometimes the winds speed up around Antarctica, and the stronger they go, it's like the water going down the plug hole, and it pushes the front. No, sorry, it doesn't push. It pulls the frontal systems in closer to the Antarctic pole and away from southern Australia. But if the winds slow down around Antarctica, that allows these storm cells to come up and come closer to southern Australia. And so the triggers are closer to us to cause it to rain. What's interesting about the southern annular mode is as a phenomena, it changes its behaviour depending on whether it's going on in winter or summer in Victoria. So when we have a positive southern annular mode in winter, that's normally pulling the frontal systems further south, and we get drying, in particular in the southwest and south of the divide. It's not to say that it can't occur in northern Victoria, because it certainly can, but just as many times, sometimes it doesn't. It's not the strongest driver in the north, but it is south of the divide. And you can see that gets into Tasmania and Bass Strait as well, in the southwest tip of WA. When we have a positive southern annular mode pulling things further south in summer, ironically, and also in spring, particularly in southeastern Australia and also around Mallacoota, a positive southern annular mode at that time can cause it to be wetter with stronger easterly flow coming in from the coast during that time. The opposite happens in winter. If you have a negative southern annular mode, you get wetter in these zones. And if you have a negative southern annular mode in summer, you often get drying. And it might come as, well, not necessarily a surprise, but the summer of 2019 was not only El Nino and La Nina El Nino and positive IOD leading into that summer, but we had really negative southern annular mode over the summer time of that period, which caused drying over on this east coastal area, and the horrific fires that ensued did not benefit from that. This is the sort of graph that we have of the southern annular mode. You get a daily reading, it bounces around, it does things for a week and comes back and then does another thing. This is the 2009 winter, spent itself essentially positive, below the line. Sorry, not positive, I'm talking rubbish, negative. 2009, a negative southern annular mode for much of winter. But you can see it's not negative all of the time. It reverts back to normal. It comes back in sort of weekly pulses, I suppose. What's interesting about the southern annular mode is its predictability only goes out about 14 days. So it's often something you can kind of look back historically and go, well, that's probably what caused it, as opposed to something that's particularly good for looking many months ahead as to what its influence might be. The positive southern annular mode, this is, interestingly, this is 2010. So this was the winter of 2010 leading into the La Nina, which was really quite dry. It was really quite dry through Victoria until that late La Nina kicked in late spring, and then the tap really turned on. But that's, there's almost a full 3 months worth there where it never got below the line. That's a very strong signal indeed. So winds spinning very fast around Antarctica, pulling the systems further south. But as I said, this phenomenon is a pretty blunt stick, because it might be happening just about everywhere like that, but just around Australia or southern Victoria, it might be a bit different to that. Or it might be different that at Argentina, even though it's saying it's positive everywhere else. So it's not always the be all and end all in terms of being an absolute distinct thing. I haven't got the data here for how the historic rainfall has been affected by the southern annular mode. You'd have to, pick locations like Portland or Cape Otway to get the best kind of influences. And we don't have data back historically before 1957. But it's once again, though, it shows a spin up of the odds greater for, well, drier in the case of positive, but once again, there is the occasional year where the exact opposite has occurred. Now, we're talking irrigation. There's been absolutely no talk of irrigation up until now, Rob. So what we've got here is we've got access to the Goulburn Murray water data, which is based on the MDBC modelling. It includes the historic and model data back to 1891, I think it is. I think we'll see. And so what we've got here is just the monthly Hume Dam inflow, not including the Dartmouth or Snowy releases. So basically the historic Murray River coming into Lake Hume. And you can see that is a June to November system historically. The median data shows the same pattern and isn't dramatically different. And it's interesting when we get to some further, I won't show it today, but when you get to further western catchments like the Loddon, Avoca and the Campaspe, their median flow is almost half of what the average flow is, indicating that system is very much strongly skewed by very dry and very wet events. And the closer your average is to your median data, the more it's not skewed by outliers, in particular really wet or really dry. So there's some data here. I reckon the average irrigator has never seen this data in their life, and I think that's a pity. I think this is really interesting. So we're looking at March to February, so includes kind of March right through until the summer, where sometimes we see ENSO activity occurring over the summer to include that. The average is a little over 2,500 2,500,000 megalitres. And the wetter years than the average are in blue and the drier ones are in red. And when you get to the bottom of here, this data here goes across, that's a 600,000 megalitre inflow year there in 1902. You can see the dries and the wets. You can see it's all over the shop. You can see that period in the 50s and the period in the 70s and a period in the 90s were very significantly wetter periods of inflow. And then we got into the millennium drought. You can see the World War II drought here, and you can see the Federation drought here as well. You can see 2022 sticking out there, but there's been wetter seasons in 56 and 1970. 1974 in particular were significantly wetter than 2022. This is just the June to November inflow, and I show that because that's the data that's more likely to be influenced by an actual climate driver rather than outside of that time. But it doesn't distinctly change much. Those 2 years were still big, but that's, as I said, they're the months that are the key inflow months that exist. Now, the real interesting stuff is when you start overlaying some of the climate drivers here, and I'm only going to be overlaying the ENSO and IOD climate driver data here historically, but unsurprisingly, it's pretty similar to Kyabram. El Nino does not equal drought in the Hume Dam, and it doesn't equal flood either. In fact, everything has been possible in that time, but it once again spins the odds up very significantly that it's likely to be in the driest third of records for both positive IOD and El Nino, and in the wettest third of records for La Nina and negative IOD. But that negative IOD, because there's probably only 1 year in the record there, I suspect we'll see, where it's been dry at the Hume Dam inflow when it's been negative IOD. And the influence of La Nina historically is nowhere near as strong as what the influence of drying for El Nino has been. This is, I think, the really cool data, even though it's a huge and messy thing. I hope you can see that on your screen. The people on a mobile device, I apologise, are in a world of hurt. But what we're looking at is all the La Ninas historically and the ranking of that rainfall, what that's actually been, not just in terciles. So interesting, about a fifth of all the La Nina years have been decile 10, very wet. And a little under half have been really wet at decile 8, 9, and 10. There's still been 3 decile 1 years though. 2007 and 8, interestingly enough, were 2 there, which were complete La Nina fizzes. If we look at that negative IOD data though, there's never been a decile 1 and 2 year, and almost a third of them have been decile 10, and more than half have been decile 8, 9, and 10. If we look at the dry end of the spectrum for the Hume Dam, a quarter of them have been decile 1 inflow. A quarter of the positive IODs have also been decile 1 inflow, but you occasionally get some decile 8, 9s and even a 10 there. 1983 was a positive IOD at decile 9. 1993 was an El Nino that was a cracker of a season as well. They're probably 2 most recent, but some of these years here are pretty iconic. 2006, 1982, 2002, 1997, 2015 in recent memory. I don't think there's too many of us, Rob, who were around who can remember 1902 and 1914. But once again, this is the value of historic data. Let's move to the Dartmouth Dam now. I'll go through this a bit quicker now that we've explained that other one. It too is a June to November system. And the median data, interestingly, there is very similar to the average data in the Dartmouth system. This is the long-term data flow from 1891. Doesn't really show quite as strongly that millennium drought period. just sort of shows wets and dries. It shows that 1917 was the wettest year ever going into that system, and 2022 was certainly wet, but there's probably been 5 others similar or wetter. This is the June to November inflow, shows a relatively similar pattern, but maybe some of those millennium drought periods there of 06, 07, 08, 09, which were 4 really dry ones in a row, and 2017, 18, 19, and 20, which is also sort of a block of 4. You've probably got to go back to the millennium drought, not the millennium, the Federation drought, to see sort of banks of 5 where it's been red in any one year after the other. The historic data for Dartmouth shows a very similar pattern to the Hume, perhaps a slightly stronger La Nina signal and an equally strong negative IOD signal there. Maybe 2 years have been drier there, which we'll see soon coming up. But, 82% chance of being in the highest third of records if you have a negative IOD, which we did in 2016 and last year. The historic data for La Nina, about a quarter of the dart inflows have been decile 10 in a La Nina, and about a third have been negative IOD, have been decile 10 there. So pretty strong swing up there. There's more than 3/4, as we showed there, 82%. Really strong swing of negative IOD for that particular catchment, and never been a decile 1-2 season when it's been a negative IOD in the dart. We look at the drier end of the spectrum. A third of the inflows into the dart have been decile 1 in El Nino seasons, and a quarter of those have been very low when we've had positive IOD. But once again, occasionally the exact opposite can potentially happen. Rightio, finally moving to the Goulburn system. This is the Goulburn, this is everything above the Goulburn Weir. So includes Eildon, includes the Acheron, the Taggart, the Yea River, King Parrot Creek, Hughes's Creek, everything that comes in above Goulburn Weir. Useless fact, Rob, is that my great-grandfather helped to build the Goulburn Weir. So I have a bit of an affinity for that. I used to catch a lot of redfin above it in my kids' time. The median data is a bit lower, a bit different. You can see there, it's not quite the same distribution in median-wise as you compare the average on the Goulburn system. If we look at the inflow data here, it tells a really interesting story. It really shows the significant influence of that, millennium drought. And, you might even say that after 2010, 16 and last year, which were wetter, there's been a large number of below average inflows into in that catchment. And we see that in the Campaspe, the Loddon and the Avoca systems as well. If you divide this data out, and I have, if you look at just Eildon Dam itself and the inflows below Eildon Dam, the vast majority of this drying signal has come from below Eildon Dam. So what we'd call the lower altitude catchments. The higher altitude catchment of Eildon itself doesn't show that degree of drying, but the lower altitude catchments like the Wimmera River and the Avoca and the Loddon and then Campaspe and things downstream of Lake Eildon show this quite significant drying over time, and clearly wetter periods in the 90s and the 70s and the 50s. This is the June to November flow. It doesn't really change the equation that much, but as bad as last year was, there was 1, 2, 3, 4, 5, it's been 6 years kind of more than that. And once again, that 1917 year really peaks out as being quite an amazing flow year. The data for the Goulburn system, once again, very similar, showing the same sort of differences compared to normal. And if we look at the historic data, well, these numbers start being not quite as big as they were for the other two systems. So only about a sixth of the La Ninas have been decile 10, and there's 3 decile 1s. The negative IOD, about a fifth of them have been decile 10. So not anything really like the DART system there in terms of that system, but there literally has never been a decile 1 inflow year there and a negative IOD. The drier end of the scale, well, about a third of all the inflow years in El Ninos have been decile 1, and about a third of the positive IODs have also been decile 1. What I want to show here, people, is the months of the year where various climate drivers. So I've talked about these 3. But we've also could talk about the subtropical ridge position and strength. We could talk about a phenomenon called the Madden-Julian oscillation, which is a tropical wave cloud that goes along the equator. And we've looked at the sticks. We've looked at a lot of scientific papers here, Rob, and we've looked at the data. And when this phenomenon is in existence, there's a tick in the box in the months where it's significantly changed the rainfall more often than not. And so we can see the various months and the drivers where that has happened for both the Northern Country, North Central, and the Northeast region. You can see, you know, I would argue, I don't think there's any difference between the North Central. No, there's just a little bit of difference. There's a tick in that box there, and I think that's the only difference, and there's one there. What you will notice from this graphic is that March and April, and for that matter, May, are missing in action. And this has always been the case. This is the autumn predictability barrier that exists in Australia, when the climate drivers that are doing something in winter and spring and occasionally over summer are always in neutral mode in autumn, and usually reverting back from what they were last year, and yet to show their hand to what they might do in the coming season. And the summer data there is, to be honest, if it wasn't for the southern annular mode, wouldn't be much chop there either. So summer, in particular autumn, this goes towards predictions, which we'll talk about in next week's webinar as well, that in autumn, it is difficult to predict the future because you don't have a climate driver in activity, and you don't have a lot of signal about what a climate driver might appear in the coming months as well. So it's a critical time of the year. We would love to have a forecast at this time that was accurate, but we may never have that because of the nature of the climate, the world's climate, and what the oceans are doing at this time of the year. So I think that's summing up there, Rob, in a nutshell. Those climate drivers that I've discussed, they significantly alter the odds of the climate, both in your local area and particularly in the catchments, but they don't guarantee anything. Anything's been possible historically, but they absolutely spin the odds up of things going in particular directions. Ignore the media noise in autumn, unless you've got a climate driver that's actually in existence, which is usually never. 2015 was a case in point where we did have an El Nino in late May of 2015. We actually had a proper one formed, but that was very, very rare to get them coming in that early. Those climate drivers, they're complex phenomena, and they're the oceanic depths and surface and atmospheric winds and pressure and cloud. And unless all 5 of those things are singing from the same hymn sheet, you don't have a fully functioning phenomena. And it's highly likely that when the opposite has sometimes happened, that we haven't had a proper phenomena necessarily changing things. Or perhaps the ocean temperatures to the north of Australia have not made the change that they would normally have done. So it's interesting. The current pattern we see at the moment, where we do have an El Nino of sorts, we have the pressure patterns thinking they want to be El Nino. We have the ocean at the surface and the depth wanting to be El Nino, but we do not have the cloud patterns and the trade wind reversal going on that is in that would be indicating a proper event. So it's what's called uncoupled as opposed to coupled. But I'll stop there, Robbie, and happy to take any questions if there are any.
Fantastic, Dale. You covered a lot of ground there, and there was a lot of gems and good information there, and I think explained it really well, and it's great to have it contexted in what the current situation is too. We have got quite a number of questions. We'll see how we go fitting them all in, but just a reasonably quick question from Kathy is a Dartmouth Dam inflow based on stream flow in the catchment prior to the dam being built?
Yes, so that correct. Obviously, the dam was built in 1970, so you can't have data going back that time. So that, yes, so previous to the dam being built, exactly right. It's using a model to model the inflow into that area. The reason that 1891 is taken is because the Goulburn Weir was built in 1891, and you have actual flow data over that weir right back to then. You got real data. But obviously, Lake Hume was a bit, I can't remember, when was Lake Hume, Rob? That was, is that the 30s, 40s? Can't remember. Pop quiz.
I'm not sure.
Someone will know. Someone will know. But you're right. So there's real data for some, there's real data where it exists, and then it's modeled back there. And you're right, you're looking at rainfall and records to actually allow that to happen. But it's but you've got all the years of real data and rainfall to make those statistical correlations that allow you with pretty good accuracy to go back in the past and make assessments of what the flow would have been.
Fantastic, and it's great to have that data too, Dale, and reasonable correlation there with the different climate drivers and the inflows, but just keeping in mind, I suppose they are just probabilities and not certainty. Question from Nick, is Enzo and IOD just cyclic, or do we have any idea about the larger processes driving these?
They're essentially random, but because they happen 25% of the time for the La Nina and El Nino, and half the time it's doing nothing. They are cyclic in nature, but what's interesting is that the La Nina phenomena is an accentuation of the normal state, and because of that, if you have a La Nina, 50% of the time you get another one the next year. Really common to have a double up, and we've just had a triple up, of course, and we've only had 3 of those historically. We've now had 4. But it's very, very uncommon to get double El Ninos, because the El Nino is a reversal of the normal state, and it's very hard to keep something reversed going forever. It wants to revert back to the normal state. And so, yes, it's difficult to get El Ninos doubled up. I think we've had a couple of those in the past. But what you find cyclically, though, is that people go, oh, you often get a good season after a drought. Well, that is sometimes based on truth, because many of the times you've got a La Nina system. Well, let's say you've got an El Nino system that's a serious one. It's very cold to the north of Australia. It's very warm out in the central Pacific. But that cold water that's up there north of Australia is now prone to being switched across over to the South American coastline, where it now pops up cold, and bingo, you've got a La Nina in the next year. And likewise, when you've got La Nina like we've just had, is that swings the odds of potentially getting El Nino either 1 or 2 years after that, because we've built up a massive amount of heat in the Western Pacific, which is prone to being blown underneath and across and over to the other side, because people may not know the Pacific Ocean sort of tumbles around in a anti-clockwise fashion. Water sort of gets downwelled down in the Western Pacific and goes across and comes up into South America and up, and then the trade winds blow it across the top. So it's I'm going to go, it's going this way, but I reckon on your screen it's going to be going the other way. But what happens in the Western Pacific often ends up in the Eastern Pacific, which is why you sometimes get those, well, they're not predictable necessarily, but you often get them where they flip from one to the exact opposite in the space of a year. I'm not sure if that's necessarily answered, Rob, the answer there for Nick. The other question there, another thing is there is a phenomena called the PDO, the Pacific Decadal Oscillation, where the south, well, it's the Northern Hemisphere Pacific, but in the southern section of that seems to spend a 30-year period where it's spending more colder water or more warmer water. And there's some belief that that sort of gives some of that periodicity that we've seen, that, you know, the 50s and 70s and stuff were a wetter time and then things were drier. But the problem we've got is that we're currently kind of in the PDO phase. We were in the millennium drought where we should have been getting water, but that wasn't happening. So that's something, it's a pretty blunt stick, I think, that Pacific Decadal Oscillation, and I'm not 100% convinced myself of its usefulness for Victoria in particular. May have something better to add for Queensland.
Thanks, Dale. I thought that was a really comprehensive answer. A question here from Andrew. Dale, I saw something recently that said sea surface temperatures were the highest they've ever been at a really general level. Does that mean more evaporation and just more rain?
Great question. So you're right. The sea surface, if I showed a sea surface temperature for right now, there's almost orange and yellow everywhere and no blue, very little blue. And the ocean temperature in particular in the Coral Sea to the northeast of us is very warm. And for most of last year, it was a record temperature. In October of last year, it was a record temperature at the Coral Sea, and it was our turn to get some record evaporation and get a moisture stream coming down of a record number. But previous to that, parts of Queensland and northern New South Wales had been enjoying, in inverted commas, those record evaporations and moisture feeds coming in. And our colleagues across the Dutch in New Zealand, they've had 4 beltings from that really warm ocean up there in the Coral Sea. But the person is correct. The warmer those tropical oceans are, the more evaporation there is and the more moisture there is. Unfortunately, that's only one of the factors for us, and we have to have the right trigger coming across to get a connection. But we would expect, well, last year, this summer, and now I'm certainly seeing record amounts of world evaporation, world rainfall. It's just that most of that falls in the ocean, Rob.
Right.
Most of it falls in the ocean. It makes the ocean less saline at the surface, which affects things as well. But if it's landing on if it gets on a landmass, you still need if you're in the tropics, yes, you'd be getting more rainfall. But if you're down in the southern areas, it's only half the question. You need half the problem. You need to be getting fronts and lows coming across, which it may not seem obvious, but when we have El Nino and positive IOD, the positioning of a big blocking high over the Great Australian Bight and over Victoria is the method by which those two climate phenomena prevent us getting a connection to the tropics. So not only is the moisture in the tropics less in those climate phenomena normally, but we also have something that stops the triggers as well. And so that's going to be the bogey for me in the coming months, is to see what happens with pressure, because at the moment that is behaving itself and going beyond itself to making it rain. But that may not be the case if a proper El Nino or a positive IOD kicks in and we start being dominated by high pressure.
Fantastic, Dale. Another very comprehensive answer. Yeah, so I'm just pretty aware of the time, and it is 2 o'clock, and I think people will be keen to head off. And I realise that you're very busy too, Dale. This has been the second of 3 presentations you're doing today. Just a reminder to people, if you could do that poll on your screen at the moment, that would be fantastic. We really do value your feedback, and appreciating the photo there, Dale. But thanks very much for today's presentation, Dale. I really thought that was great and very informative. Yeah, I think most people would have got quite a bit out of that. And again, if I realise that was a lot of information to cover, but if the recording should be out next week, so if you want to follow up on that, you can go for your life. So thanks very much to Dale for a great presentation. Thanks to Joe, who's been beavering away in the background to try to make us look good. So thanks Joe, and for your pre and post webinar work that you are doing, and a big thanks to all the webinar participants for your support, and thanks for your contributions. So thank you, and have a good afternoon, and look forward to catching up again in part 2, same time, same place next week.
Yeah, we'll sort out what it means in terms of the modelling and actually using this information to making decisions.
Fantastic. Thanks, Dale. Much appreciated. Have a good afternoon.